Hello everyone and welcome back. Today I'd like to discuss redox reactions, which are oxidation-reduction reactions. And just to start us off, let's review some basic concepts that will really help us along today in describing and understanding redox reactions. And that is the concept of oxidation numbers. Okay, so I'll remind you that these are not actual ionic charges. They're just numbers that we ascribe to individual atoms within a molecule to inform us what they would formally have if they were to react, or to help us understand sort of the electron distribution within the compound. So it's not necessarily, it's just for bookkeeping purposes. And we did this last semester when we described redox reactions when we introduced them. So oxidation numbers, as just as a quick review, if you have neutral compounds, we usually say that they are always zero oxidation number because they have a neutral charge. If you have a polyatomic ion, the charge of the ion informs you of what the oxidation number of the entire ion is, and then you can try to break it up for within it. Oxygen is typically -2. And then anything in that group 6A is usually -2, group 7A is usually -1, things like that. And I encourage you to go back and review this concept if you feel a little bit rusty, but those were just a little bit some of the rules. And so let's just dive into a quick example. Try to ascribe the oxidation numbers for iron and for oxygen in this compound. Okay, so take a moment and try to do that. Okay, so oxygen, as I just mentioned, is typically -2. So we will use that as our rule to try to figure this out. So if oxygen is -2, then 4 oxygens will be -8. So this half of the substance here is -8, and therefore this entire thing should be +8. So then I would say that Fe3 should be +8, and therefore Fe would be +8/3, and so I can easily put that oxygen is -4, and this one is 8/3 for each individual oxygen and for each individual ion. Okay, so that's pretty quick. Hopefully it gets you a little bit more comfortable because we're going to be using quite a lot of oxidation numbers today. Okay. Now, jumping right into redox reactions. So we have oxidation, reduction, and then often that is shortened to redox. Okay, and a quick definition for this is just an electron transfer from one species to another. If you see reactions where you see an electron transfer, chances are it's a redox reaction. Now you can see I wrote here oxidation reduction, and that is because these things usually go, not always, they always go in pairs. They must go in pairs. You cannot have oxidation without a reduction. So you always have 2 reactions going in tandem, going simultaneously, and so these go in pairs. Alright, so what we will do now, I will give you an example of a redox reaction, and we will try to balance it using some concepts that you already know and some concepts that you'll be introduced to today. Without further ado, let's start with that. So if I have the following reaction: copper, elemental copper, reacting with silver nitrate, which is aqueous. This will result in copper nitrate and elemental silver. And what I'd like to do, the overarching theme for the next few minutes, would be to try to balance this and to try to understand some of the nuance ideas here. And so, as I mentioned these go in pair. Let's try to see why that is. Before we begin, again, let's try to ascribe oxidation numbers to each one of the elements here. Don't worry about nitrogen and oxygen. Just do NO3 as a whole, and then try to do for copper and for silver. All right. So as we mentioned, if it is elemental or neutral compound, it will have the oxidation number of 0. So both copper and silver here will have 0. All right. Again, nitrate from the polyatomic polyatomic compounds that you had committed to memory, NO3 would be -1, and same here is -1. Therefore, I have a -2 here for both of them. That will then mean that silver will be +1, and copper here will be +2. Okay, so hopefully a quick review for you, and so that's about it. So that, as you can see right away, copper here goes from 0 to +2, meaning its oxidation number was altered, and same for silver. The oxidation number for silver went from +1 to 0, and its oxidation number was altered as well. Nitrate did not. It's -1 here and it's -1 here. The reason I wrote -2 is because there's 2 of them. So NO3 is just a spectator here in this reaction, and many people would also omit that. So you can certainly write it like so for the oxidation reduction reactions here. You can write it like this. Okay, and you can just omit that, and then at the very end you can bring it back. Okay, so if I'm looking at this type reaction right here, which is what we're going to be focusing on, if I were to ask you if this was balanced or not, you might be tempted to say, well, yeah, I have 1 copper here, 1 copper here, 1 silver here, 1 silver here. Yeah, it looks balanced, but it isn't. So it's misleading. And just a quick look here with the nitrates, you can see that it is not, because the nitrates are not balanced. So we're going to try to balance this. All right. And what I'm going to introduce to you right now is the idea of half reactions. So if I have this as the overall reaction here, what I propose is that I can break this up into the two pairs of reactions that constitute this. Okay, I have copper doing something, and I have silver doing another thing. So I can break this up. So I can say I have 2 half reactions that together constitute the entire reaction. And it will be as so. Copper, solid, will go to copper +2, and this is aqueous. Okay. And I have silver, aqueous. It is also going into elemental silver here. All right, and let me get rid of this. Okay, so that's where we are at the moment. And what I'd like for you to also tell me is another type of review from chapters ago, is which one of these is the oxidation half reaction and which one of these is the reduction half reaction. Okay, so take a moment to try to tell me this or figure this out. Okay, as a reminder, Leo the lion says grr. If you forget, sometimes I even use that too. That's not like you don't have to necessarily remember this if you don't deal with this on a daily basis. Electrochemists, people that do cell batteries and things like that, they know this is second nature to them. But people that don't deal with this on a day-to-day basis, they use this mnemonic, with no shame. So loss of electron is oxidation. So meaning that something that lost electrons became more positive. So copper here became positive, meaning it lost electrons. So this will be my oxidation. And gain of electrons is reduction. I know it's an unfortunate thing, gaining is reducing. So gain of electrons is reduction, and that will be it here. So one more thing I'd like you to do is try to assign electrons to each one of these half reactions to try to balance the charges. It's not important to just balance the masses, but also the charges. So if you look here, the overall charge on the reactant side for the copper is 0, and here it's positive 2. Here it's positive 1, and here it's 0. So what I'd like to do is try to introduce electrons to try to balance it out. Because electrons have negligible mass, it's not like I'm doing anything, and then eventually I'm going to cancel them out anyway. It's for bookkeeping purposes. So if I'm looking here, I want to have 2 electrons being added to this side. And 2 negatives and 2 positives will cancel it out. If I'm looking here, I want to have 1 electron here to balance the positive 1. And so these two will be my 2 half reactions with the electrons ascribed to each one of them. All right, great. Now to complete the balance, I'm not done yet completely. As we said, these are half reactions. I get to add them up to get the whole. Before I can add them up, I just mentioned to you that these electrons are for bookkeeping purposes. They're not actual species. I can't have them in the total net reactions at the very end. So if I were to add this right now, it would look as though they're there. So I shouldn't. So what do I need to do to try to get rid of these electrons when I add them up? Right, so it would be to multiply this through by 2. So if I were to multiply this through by 2, I would have 2 electrons, 2 silvers here as such, and then I can add these 2 reactions together, and then you can see right here, the electrons on the left side will cancel the electrons on the right side, just like a mathematical equation, and I can add this up and get the full net reaction that I need. And I can add back the nitrate or whatever spectator ion I want at the end of it if I want to. And so this should be my reaction at the end. Okay, and so as you can see here, I have 2 silvers and I have 1 copper. This was fairly simple. It only took forever because I was holding your hand going through this, but it should take you a few seconds to get to here from the original reaction. Okay, and so if this under neutral solutions, neutral conditions, this is the methodology by which you would go about balancing reactions, redox reactions. Fairly simple, but it gets a little bit, just a hair, more complicated if you have these redox reactions occur in basic environments or in acidic environments, which many batteries, alkaline batteries, are in a basic environment. So a more realistic scenario would be for electrochemical purposes, for thermodynamic purposes, for engineering purposes, would be to discuss this in non-neutral environments. So I'm going to give you some sort of like a recipe, a step-by-step guide to balancing redox reactions, and then we'll go through an example to really showcase what's happening. So because it looks a little bit daunting after we look at that. So let's do that. Let's do balancing redox. Okay. So balancing redox reactions. All right. As I said, I'm going to give you like a little bit of a recipe. And so first thing first, what you're going to do is using oxidation numbers. So you want to ascribe the oxidation numbers to the different species. Separate the reaction that's given to you into 2 half reactions. Okay, so that's the first thing you want to do, right? Afterwards, you want to balance all the atoms. Except oxygen and hydrogen. So we didn't encounter oxygen and hydrogen in the previous example, but we will now. So if you have neutral solutions, you can go ahead and skip to step 3. Okay? If you have non-neutral solutions, so whether it's acidic or basic, doesn't really matter, you need to do the following 2 things. 1, for every oxygen that appears in the half reaction, to the opposite side you want to add waters, H2O, to balance that oxygen. So add enough H2O molecules to balance any oxygens in the reaction. And this has to be done to the opposite side. Okay? If I were to put them on the same side, then I would just add the same. I would just double my oxygens. So I'm trying to balance the oxygen, so I would have to put it on the other side. Okay? Now I introduce a whole bunch of hydrogens, and I may have other hydrogens anyway in the reaction. To balance hydrogens to the opposite side from where they appear, add enough H plus to do that. So add enough H plus to the opposite side to balance hydrogen. Okay. So we didn't do this. I promise we'll do this in a few minutes. So after you do this, you go to the next step, which is to ascribe the number of electrons to each half reaction. So ascribe the appropriate number of electrons to each half reaction. And we just did that, so you saw what that's like. Okay. Then what you're going to do is adjust the coefficients. Again, we just did this. Adjust coefficients of for each of the constituents in the reactions, so that the number of electrons in the reduction half reaction is equal to the number of electrons in the oxidation half reaction. Okay, and that's just, again, we just saw that. I don't want to have oxygens in my net reaction at the very end. I want to make sure that both half reactions have the same number of electrons so they cancel out. That's what this does. All right. Then after we do that, add the 2 half reactions together. Okay. And after you add them up, simplify if you need to. So, you know, if it ends up that they all have, I don't know, if it's the coefficients are 4, 2, 2, 2, you can divide through by 2. Something like that. Or if you have something that's a little bit messy, you know, with ions that can get easily combined, we will do that. We'll look at an example to show you. So if this is true for acidic and for neutral, if you have a basic solution, I'm going to add one more step. You don't need to do this for acidic solutions or for neutral solutions. You only got to do that for basic media only. And so what you're going to do here is add enough hydroxide ions to both sides of the equation to offset H+. Okay? So add enough hydroxides to both sides of the equation to offset H+. Okay? Now, after I offset the H+ and I have the OHs there, I want to clean it up a little bit. So if I have H+ and OH-, on the same side, I can combine them to water, things like that. And then I also want to simplify. So now I know this is reduxulous, so let's go through an example and it will be a little bit more apparent. This looks pretty daunting. But it's because I'm slowly explaining things, and that's usually what it is. You know, you've seen this in the past when I explain something that looks dense, but when we're actually doing it practically, it doesn't take as long, and it becomes pretty apparent what I mean. Okay, and after we do an example, when you look back at this recipe, it will make sense. You'll remember the example pretty well, hopefully, or the steps that we did in class, and you'll be able to apply it for yourselves. So that's my goal, at least. So let me get rid of this, and we'll go through an example. Okay, we'll go through a disproportionation reaction. So in this example, and it will be a basic media example, I will have bromine. So elemental bromine disproportionates into bromate and bromide. Okay, in basic environment. Okay, in the basic environment, and I want you to balance this. Okay, so let's write out the reaction, or what we're using. And so I have elemental bromine, which is a liquid. This will disproportionate itself into bromide, be aqueous, and bromate, like this. Okay. All right. So we have the reaction, and now let's go through step by step what we do for each one of the steps that to get to the balanced net reaction. All right. So first thing is we want to ascribe the oxidation numbers here, because we're going to have to split this up into two half reactions, and so we need to understand which one is the oxidation, which one is the reduction. So this is elemental, so it'll have a charge of an oxidation number of 0. This one is an ion, so it will have the same as the ion itself, so it'll be -1. This entire guy here will be -1, because it's negative from the negative charge for the ion. Oxygen, remind you, is -2, and so 3 oxygens will be -6, so this whole thing is -6. This side, the bromine, has to add to the -6 to get -1, and so it would have to be +5. So that would work. Okay, now I'm ready to break this into two half reactions, and I chose this. I like to choose the most esoteric type examples, because if I give you a simple example and you see something a little more complicated later, it may daunt you. So here I only have one reactant, so it's a little bit esoteric, and what I mean by that, this bromine here does both. It gets oxidized and it gets reduced, so it disproportionately. And so I will have an oxidation half reaction that has this, and a reduction that has this. So to look at this, I have bromine. I'm going to drop these for the states just for brevity here. Bromine will go into bromate, and also bromine will go into bromide. Okay, so I have these two half reactions. Which one is the reduction and which one is the oxidation? What do you think? Okay, so again, this here will be the reduction. I went from 0 to -1, and this will be oxidation. I went from 0 to +5. Okay, so that's how that would work. So now, what I gotta do now is try to balance this. First things first. I'm going to balance the elements that are not oxygen or hydrogen. I have oxygen here, so I'm going to ignore it for now. And I'm going to use bromine only. So I have 2 bromines here. I have 1 bromine here, so I'll put 2. I have 2 bromines here, 1 bromine here, I'll put 2. That's the first step. I'm going to do that. Right, great. Now, I need to balance my oxygen. And we mentioned that we use water to balance oxygen. If I were to put water again on the same side as the oxygen, I'm just doubling the number of oxygens I have. So that doesn't make any sense. So I'm going to put oxygen on the opposite side. So I'm going to put water on the reactant side of this reaction. And since I have 6 oxygens, I'm going to put 6 waters this way. 6 H2O. Alright? And for here, I don't have to do anything. Okay? I don't have any oxygens. Great. Next step would be to balance the hydrogens. I don't have any hydrogens here. Again, I'm going to ignore this. This here, I have 12 hydrogens on the left side. So I got to add enough H plus to offset any H's that I have in the reaction. So I'm going to, again, add that to the other side to make sure that I have the same number of hydrogens on each side. So I will add 12 H plus to the other side. So now my oxygens are balanced, my bromines are balanced. So both reactions are happy from an elemental perspective. Next thing now, so this was the step 2 that we didn't do before. Now step 3 is to try to put enough electrons to each of these to make sure that that the charges on each side are equal. So here, let's look here. I'll use red again. I have 2 negative here, negative 2 on this side, and I have 0 here. That must mean that I need to have 2 electrons on this side to balance this. So I have negative 2 here, I have negative 2 here, that's good. Here, this here is neutral. Here I have negative 2, here I have positive 12, so I have a total of positive 10. So I need 10 extra electrons as such. So now I have the charges also balanced. Okay? The next step now is to try to add it up, but I can't add it up because I have 2 electrons here and I have 10 electrons here, and if I added it up, in my net reaction I would have 8 electrons on the right side. I don't want that. I want to get rid of all the electrons. So to do that, I need to modify the coefficients here to make sure that I have 10 electrons. So that's pretty simple. I'm just going to multiply everything through by 5. And if I do that, if I multiply by 5, I get 10 here, I get 5 here, and I get 10 here again. Okay? Now I'm ready to add it up, because when I add this up, lo and behold, the electrons would go away when I add this up. So let's try to add this up. When I add this up, the electrons go away. I have 6 H2O right here. I have bromine and bromine again. I have 1 and 5, so together I'll have 6 bromines. Okay? And then this will go into, I have 2 bromate. Okay? 10 bromide. And I have 12 H plus. And so this is almost done, but this is pretty much the balanced reaction. The last modification is to simplify this, and so I have an excess factor of 2, so I can divide through by 2, as you can see, to simplify this. And so I'll do that. So I'll divide all of this by 2, and so 6 becomes 3, and 2 becomes 1. 10 becomes 5, and 12 becomes 6. And so this is my balanced reaction as it stands, okay? Now, I mentioned right here that this is occurring in a basic environment. If I were to tell you that this thing occurs in an acidic environment, you'd be done, that's it. Okay, that'd be the end of the problem, that'd be the end of the balancing act, you'd be done. For a basic environment, I mentioned there's a slight complication, so let's go through that and see what happens. So I mentioned that for each incidence of hydrogen, of H+, every time I see an H+, I want to offset that with an OH-, with hydroxide, okay? So don't look at the H2O here, the H doesn't matter here, I'm looking at specifically charged hydrogens. So I have 6 H pluses here, so what I'll need to do for basic, for the basic modification is to add 6 hydroxides to offset this charge. Okay, now I just introduced oxygens and hydrogens on this side. I want to do the same thing on the other side because I want to make sure it's, 6 OH minus. here on this side. Okay, I want to make sure that